Okay, equipotential surfaces. Here we're going to try to visualize what the electric potential profile looks like around different charged objects. And basically, equa means equal, potential talking about voltage. We're going to look at surfaces around a particular charged object, and these are surfaces that represent all the same potential, 10 volts, 100 volts, whatever that might be. Now the work for a charge, the work on a charge due to an electric field is equal to negative Q delta V. So if you're on an equipotential line, moving a charge on these equipotential lines does no work on the charge. And that's very important here, that there's no change in energy, there's no work being done. It's really locations of equal amount of electric potential, equal amount of potential energy. So we look at a conductor, and we know that the electric field in a conductor must be zero. Faraday cage is an example of a conducting enclosure where there's no electric field within it. We know that the charges must always sit on the surface of these. Therefore, on the surface of any conductor, we're always dealing with an equipotential surface. The surface of a conductor is an equipotential surface. So whatever the voltage is of this conductor, it's going to be the same all around. Okay, parallel plate capacitors, on the plates, the voltage is the same no matter where you are on the plate. Same thing, no matter what the shape of the charged object is, the conductor is, that's charged, you're going to have basically an equipotential surface around that. And going from there, we'll surround it with similar surfaces with the same type of symmetry, and they are always perpendicular to the electric field lines. So once again, equipotential surface is a surface on which all points are the same potential. All points, therefore, for any charge will have the same potential energy. No work is required to move a charge at a constant speed on an equipotential surface because there's no change in kinetic energy. Okay? You're not exchanging potential energy for kinetic energy. Here are equipotential surfaces around a point charge. And if you remember, one of the homework problems actually had you calculate the radius for different potentials around a particular charge. So around this type of object, okay, a point charge, a spherical charge, you are going to have spherical equipotential surfaces surrounding it, where each surface will have a slightly lower and lower, progressively lower electric potential. So maybe here we're at 100 volts, maybe here we're at 50 volts and 25 volts, 12 volts, 12.5 volts, so on and so forth. Now, if we draw our dipole, okay, we remember how the dipole works. We have the electric field lines pointing from the positive charge to the negative charge. To construct our equipotential surfaces, they will always be perpendicular to these field lines. So here we can see at the very center of it, you're going to have an equipotential surface or line, which represents, if these are equal and opposite in charge, 0 volts. As you get closer and closer to the negative charge, you get more negative voltage. As you get closer to the positive charge, a more positive voltage. But again, notice all of these dotted lines are always perpendicular to the red electric field lines. The electric field lines are perpendicular to the equipotential surfaces. So one of the labs that we do is called equipotential. You actually map out with the galvanometer where the equipotential surfaces are, and then draw the field lines perpendicular to those surfaces. And again, here's a close-up of our dipole, and the green lines represent the equipotential lines, the red lines represent our electric field. For a parallel plate capacitor, we know from Gauss's law that the electric field was constant. Here we can see going from 100 volts down to 0 volts, from a positive plate to a negative plate. The active potential lines are pretty much parallel to the surfaces, okay? Right at the surface you have 100 volts, a little bit, about 1/4 of the way, 75 volts, in the center 50 volts and 25 volts. But notice as we start getting around the edges, there's a little bit of curvature right there, and that causes the electric field lines to curve also. Okay? But again, there's our parallel plate capacitor, great example for a constant electric field. And again, if we're mapping the equipotential lines, also perpendicular to those lines, so everything has a very nice symmetry to it. One last thing, sometimes you'll hear the term electron volt. An electron volt is not an electric potential, but rather its amount of energy. If the potential difference is 1 volt, and we place an electron in this 1 volt potential difference, that electron, having a charge of 1.6 times 10 to the minus 19 coulombs, and the volt being 1 joule per coulomb, that will mean that the electron will accelerate and get an energy, mechanical energy, of 1.6 times 10 to the negative 19 joules. So an electron volt is a very, very small amount of energy. It's the amount of energy imparted to an electron if it's placed in a 1 volt potential. This is a very useful unit because oftentimes in both electronics, well, mainly if we're talking about optoelectronics, when we're dealing with LEDs and things like that, or in the case of radiation, we'll talk about particles in terms of how much energy they have in electron volts. So for instance, typically when we're dealing with visible light has an energy roughly around, I don't know, about 5 electron volts if you're right toward the center, which means that in an LED, if we're putting a certain voltage across it, we'll get that electron to accelerate. Well, we'll get the electron to have work done on it. Then the electron will give off this energy in the form of light, and this light will be equal to the amount of energy that the electron was able to get by going across the LED. In X-ray machines, most of these X-rays are measured in kilo-electron volts, or thousands of electron volts. In that particular case, we're accelerating an electron with across a very high potential. It hits a hard metal target, usually made of tungsten, and then X-rays are given off equal to the amount of energy that the electron had. The electron was probably accelerated to at least 100 through 100,000 volts. So therefore, the electron will come in with a few 100 kiloelectron volts of energy, giving off an X-ray with an equal amount of energy. Finally, with gamma rays, these are typically electromagnetic waves from the nucleus. To compare them to X-rays, we'll also measure them in kiloelectron volts or even mega electron volts. Okay, so electron volt, very, very important unit, especially when we're talking about interactions where an electron gives off its energy to become an electromagnetic wave.